We will review the chapter. We'll review chapter 4. I don't know what happened. We'll review chapter 4. Let me get my pen. Review chapter 4 on power transistors. This is for course 4242, power electronics. And we would review those basic, very essential things. But I suggest that you should do some work. You should review at least the videos on this, the worked out examples. There are some using a MathCAD files. There are some videos which I expect that you should review them before you review these videos. Now, the MOSFET is a device like if you put a gate to source voltages, you're going to have the drain current. That is as long as that the gate voltage is greater than the threshold voltage for an NMOS, that you expect. That means the voltage dependent device. You put a voltage, your output will be current there. And this is for N channel. Is the opposite direction. Now, what is important to know that if you drop that characteristics, the drain to source voltages to the drain current, and then this is the load line, which is the load line VDD, which is the supply voltage divided by RD. And then as you increase the gate voltage, gate to source voltage, if you increase that, and then this characteristics goes up, that this goes up this way. Now, what is that? If you want to have use as an amplifier, normally you work in this area, amplifying area. On the other hand, we'll be using this MOSFET as a power MOSFET as a switch. That means we'll be using somewhere on that side, so there is a switch there. Voltage drop across the switch is small there, and that's basically is that. But just to but normally, if you be using an amplifier, you should use this equation, like the drain current is a function of this gate to source voltage square law. But the question comes that if you are working as a switch, you will be driving hard. It will be like a switch. You may not be able to use that expression anymore. Like some of the things we should mention is very important. If you look through the MOSFET, the device itself, there is a MOSFET here. This is an NMOS there. There is a capacitor between the drain to the gate and the gate to the source that limits that the turn on time of the device and turn off time also. There is also internally that if you can look through, there's also internally there's like a NPN sort of a device there. And then also, because this is an PN junction, there you expect some capacitance, the drain to the source, and also a resistance between that base to the emitter there. This is the character there. But there is also, what it happened that very often that you're going to find that this is normally very small, it's like a diode, and then as a result you have like a P to N, there is a diode there. Internally you can see that look like the device has an internally diode, in the reverse direction. The forward direction is a switch there, the reverse direction is a diode. But what does it mean? That it is not it can allow current in both directions. That's the direction there. And that is a MOSFET. Now, what happened that very often if you apply a current like a 10 amps, like a 10 amps or 100 amps, and then if you have an inductive load, you expect that there will be this diode, and this diode will act like a freewheeling diode, but this rating of this diode will be much smaller than the transistor itself. As a result, you cannot rely on that diode to do the freewheeling action. As a result, that this is the device, this is the diode, is the built-in diode there. And then if you want to be freewheeling diode in opposite direction, you apply a negative opposite direction a diode there. That's why so that the freewheeling action is done by this D1 external down. But again, to prevent that, that the current from the transistor through this transistor is only one way, you put another diode D2 there, so that the transistor current goes from the drain to the source, and then freewheeling done by that the diode D1. This is the basic thing. That means that a MOSFET, summarizing MOSFET, can allow current in both directions. It's a bidirectional device unless you prevent it to be. The warning is that the internal built-in diode will have a much lower capacity of the current capacity than the MOSFET. That's why you cannot always rely on that, the diode, to do the function you would like to have. But as far as the switching is concerned, that that the MOSFET is a gate voltage. If you apply a gate to source voltage, there will be the drain to the source current, which is depends on the GM of the transistor, and also drain to the source. There is a small signal resistance, and also capacitor. There is a capacitor to the gate to the source. That's the switching model of the transistor. That means every time you turn on a switch, you expect some delay time of this device. Now this is a typical characteristics for a switching characteristic for any power semiconductor devices. We mentioned it in chapter 1, like this, as a switch. Like here, you apply gate voltage virtually like a square wave. Then now there is a delay time. There is a delay time of the device. There's a rise time, and there's also then the device completely conduct, and there is the fall time, and then this TF, the fall time, and then the off time. There is a particular off time you need for the device to go. But what is important to know, there's a cycle there: the delay time, rise time, on time, the delay off time, and then the fall time. These are the typical one. Like similarly, this is the gate voltage you apply. Once you apply gate voltage, because there is a delay there, remember there is a capacitor from gate to the source. The voltage of a capacitor cannot rise instantaneously. It takes some time. So similarly, when you have that, the current will not rise rightly. There is a current will be delayed. There is a delayed current will rise. There will be delay of the current too. The voltage is delay, the current will delay, and then there's the drain current. You got a delay time, rise time, and then a fall time. And then this is by definition that you can find out the frequency, the maximum frequency you can operate. The manufacturers normally, if you look to the catalog, the manufacturer will specify the rise time and then time. But this on time, it depends on that operating condition, what frequency you're operating at. But the delay time and rise time are decided by that, the devices itself. And then the fall time depends on the circuit also, what behavior you have. Okay, there's a question comes here. A MOSFET switch is a voltage dependent switch, or current dependent switch is a voltage dependent switch. That's the right answer. Now the question comes that an NMOS switch can be allowed to current flow both direction, only one direction, or the source to the drain or drain to the source. But in this particular MOSFET is in both direction current flow unless you stop it, which is opposite, which is different from the bipolar. The drain current of MOSFET depends on what? The gate source voltage of the MOSFET. It's a gate to the source. Whatever the gate source voltage you apply to the MOSFET depend on the gate source voltage. The drain current depends on that's the beauty of the MOSFET. You can apply a voltage, and then that you can control or limit that how much you can control that out the drain current by the controlling this gate source voltage. The question you got gate source voltage. In order to ensure drain current flow, the gate source voltage must be greater than the threshold voltage. You have to, not less than threshold voltage. You have to have a greater than threshold voltage. Remember that this characteristic we mentioned to you. This is the VGS, and that's the ID, and that's the threshold voltage. It must be greater than threshold voltage because you have to break that the threshold before that channel. If you look to the operation of the MOSFET, there is a channel. The channel has that it doesn't warn us. There is a gap there unless you put in the induced voltage to enhance the voltage or repel that the electrons or the holes, depending on the type, that there is a threshold voltage you need to apply for that. Like on the other hand, for bipolar transistors, if you look for a bipolar NPN transistor, that you got a collector base emitter, and then this is for this NPN. Mostly you work for power electron NPN transistor. often maybe PNP, but it's basically what is important. The emitter current is equal to the base current, plus collector current. That's very important to know. This is the important relationship. Other relationship is the beta, is the collector current depends on the beta and of this times the IB. These are some of the basic, one. It's very important to know the relationship. And the characteristic is similar. But what is the difference here? The gate to the collector to the emitter voltage depend on the base current. In the MOSFET, it depends on that gate to source voltage, but it's the base current. If you have a base current, this base current drives the collector current. The collector current is depending on the base current, but not the other way. No, if you apply a voltage here, and then and you think there will be current from this one, and then automatically come the other way. It's not. It's only one way. The base current produces the collector current, not the vice versa. And as a result, that what you're doing, like a diode, base to the emitter voltage, and the base current is like, this is the base current, like basically this is an NPN. This is like a diode. This is the diode characteristic you have. Okay. And then once you have that base current, you adjust the base current. If you adjust the base current, the collector current, they adjusted that. And then that's the one active region you operated then the transistors, amplifier, like in your electronic circuit. But here we are working as a switch there. Then we should apply a base current so that it's saturated in operation saturation region. That issue comes, how much is saturation? You give it too much or less. That's the issue to consider that. Sometimes you have to overdrive it. Like if you look at the transfer characteristic, that the collector to the emitter voltage was, if you do nothing, collector to the emitter voltage was the maximum one. As you apply the base current, then once you apply a base current, then this one slowly more current come, and the collector emitter voltage less, and that goes to the transition one. This will be active region. You operate like an amplifier. This is the amplification, is pretty much the linear region there. The saturation region, you go through that, at the end, so that the BCE, the voltage base, the collector to the emitter voltage saturated almost a small voltage. That's what you do. Like now the question comes, what is the end? You can do like just like this at this point, or you do more than that. If you do more, apply a base current, it will be oversaturated, or oversaturated, or undersaturated, or just saturated. That's why there's a factor is called the overdrive. That's called the beta F is the IC divided by IB is the forward transfer, the current ratio. That's the current ratio. Now how much you apply, more or less, that's the you saturate, oversaturation, then needs more time to recover it. Like if you want to use it as a switch, that's very important to know. We are making sure that we'll ensure that the base current is enough to drive into the saturation, is in the saturation region. Then in this case, the VC will be like a switch. That means it will be CG saturation. Like what we can find out, we can find the collector current. The collector current will be supply voltage. The DC voltage is minus the saturation voltage RC. That's the ICS. Is the maximum current it can flow through the transistor at the saturation. Okay. Now what will be that? What will be the BC? What will be the IBS, corresponding IBS? Whatever the ICS divided by the beta of the transistor, whatever the beta of the transistor manufacturer specified, that's called the IBS. Okay, corresponding the base current at the saturation. This is the collector current at saturation, base current at saturation. Now what happened that sometimes you apply more than that. That means you can find out that this is the base current you are applying. Basically, how much base current you have? VB minus B base to the emitter, divided by RB. That is basically is about 0.7. That is the voltage. That is the current you are applying. You really need, if the transistor is is perfect in terms of that the beta, then this is the one you need. But what you are applying really, it depends on the RB you have and the BB, and that's the one what you are really applying. Now this is what you need and what you apply. Okay, this is what you are. This is what you are. Uh, Need. This is what you need. This is what you are applying. This ratio is called the overdrive factor. This is you're normally applying more. This is what you are, the base current you are applying. This is the base current you need. According to that, the beta of the transistor. This factor is called the overdrive factor, overdrive ratio, overdrive factor. How much is the overdrive? You may be more, you may be less. That's the one you need to decide, the compromise. It is designer. Now the force beta, like the beta we have is a 1 beta. Now the force beta, you're forcing whatever the collector current was, whatever you are the base current you are applying. This ratio is called the force beta. Now you have the conception for normal electronic circuit. You have beta concept, the beta of the transistor, the collector current to the base current ratio. But now here we got a concept of overdrive factor, how much you need, how much you are applying, and then the ratio of that, the collector current at the saturation and the base current you are applying. That's called the force beta. That will be much lower than the beta of the transistor. If the beta is like 100, if you got a beta 100, this could be probably about 10 or 8. This could be normally much lower than the normal beta of the nominal beta of the transistor. Like this is the one we mentioned for that again and again. That characteristic is important. For a bipolar transistor, you apply a wedge voltage, the base to the emitter voltage. Look at that. There's something to know about it. Look at that. The previously 0 to the V1 and minus 2, you are applying a positive and negative voltage in this particular case. Why? And then once you apply, think about positive voltage, and then once you do that, there will be base current. There will be, although the base current will not rise immediately, then there will be a collector current. The collector current will not respond immediately. There will be delay time, there will be rise time, there will be one time, there will be storage time, there will be fall time, and so on. So that is the typical characteristic of that all the devices: the delay time, rise time, and the storage time, and then and the on time, actually keep it on, and that the storage time and the fall time. By the way, the delay time are defined by the manufacturer, and the rise time and the storage time, but the T on and off is depending on that user, how much what frequency you're operating at. But the rise time is defined from, what is the rise time? Is defined from rising from 10% to the 90% of the steady state value. If the steady state value is ICS, that rising from 10% to the 95%, the time it requires to rise, that's called the rise time. Similarly, the fall time. And then what is this delay time to rise from 0 to that 10%? How long it takes to rise from 0 to 10%. This is called the delay time. And the rise time is from 10% to 90%, and then fall time from 90 to 10, and that's so and so. Okay, this is a typical for waveform. I would suggest that if you go to this the website, you can look for the data sheets, the .com. You can find out that any transistors, the specification, especially the power transistor, will give you those the values. Like there is an example here. We see whether we can apply it. The RC is given there, VCC is given there, VC saturation is given there, and then asking you the collector current. What is the collector current? Obviously, this will be the 200 minus 1.200, 200 minus 200 minus 1.5 divided by 10 ohm. That will be the answer, right? This is the collector current of that one. That's one. You don't need the rest of the information. They ask for the collector current, ICS. That we know that voltage is given. When it is saturated, we need the supply, we need the RC, we can find out. This is the correct answer will be that. The base drive. What will be the base drive in this particular case? And let us see what is that. A VB is given. The VB is given, and then also RB is given. RB is given, and then RB is given. That base to the emitter voltage is given. I suppose base to the emitter voltage is 0.7. That means the IB we expect equal to what is that? The VB is 10 minus 1 divided by RB is equal to 1.2 ohms. That is the IB you expect, right? Please do some those exercises and different values and get some practices. Don't rely only on them. Do some numbers yourself and see whether you can figure out. Now, what is the overdrive factor? Now you know that you can find out. You can find what is the ICS. Okay, when you know what is the ICS, you can find out because you will know that VCC minus VCC minus VCE divided by divided by RC will give you the ICS, and then you can find the IB. And once you find the IB, then you can find out that this will be the overdrive factor. You can find it out. You can find out that the beta F, it will be the beta F. This will be beta of this with this working ICS divided by IB. That will be this IBS, and IBS. Once you got the IBS, then you can find out the ICS by IBS will give you the overdrive factor. Okay, please try those numbers. The force beta, you can do the same thing. The force beta will be that the beta will be that IB. The force beta will be the whatever the force beta ICS divided by this the IB will be the force beta. That's the beta you are applying. You're forcing the beta is different from the normal one, and ask you to find this value. The force beta of the transistors, all the values are given. Previous practice that. The delay time. The delay time is defined as that from 0 to 10% of the peak value. That's the one. The delay time is defined as the voltage or current to rise from 0% to 10%, not from 10% to 9% will be the rise time, and then rise from it will be the 10%, 9%. That will be the what do you call this? The delay time. The rise time is the time from the rise from 90%. Rise time is the rise. The rise time is the time for the voltage or current to rise from 10% of the steady state current. It's the rise current. The rise current is the rise current. What was this before one? It was the delay time. It was the delay from 0 to 10%. This is the rise time is from 10% to 90%. The fall time is that value from 90% to 10% of the peak value. Please remember those values are standard, the definition for rise time, fall time of that electronic circuit, digital circuit. This is the standard definition for them. The rise time, fall times, and delay time. These are inherent within any of these electronics or electrical devices. Like you are asking for a BJT switch. A BJT switch is a current dependent device, right? It's not a voltage dependent. That is the right answer. And then looking for BC operation. A bipolar normally operated as an on-off switch between the cutoff and saturation region. You apply a voltage. If you don't apply voltage, it becomes a cutoff. And if I apply a full voltage, you are operating in this saturation region. That means it is going from off to on. That is this operation line. Like in between, there is an active region. That is the region you normally operate if you are using as an amplifier. But for switching, you just switch. During the transition time, there will be some transition goes through that, but that is a short time. But you will operating as an amplifier, bias it at that the active region. This storage time depends on the how much. The more current you have, there will be more storage you got. The more base current you have, the more storage time you have. That means that current storage time depends on how much current you have, how much base current you have. The base current, if you get too much base current, you have a storage problem. It will take more of the storage time or recovery time it takes there. That's what it basically is there. Like a storage time depends on, it depends on the amount of charge, you stored within the device. It will depend on that inversely, directly on the overdrive factor. If you drive it too hard, that means if you drive a lot of base current to that, whatever the minimum you need, what is the minimum? There is, it's difficult to find out what is the critical one need. That normally you have to have a little bit more than what you need. Okay, directly depends on the overdrive factor. Storage time or storage charge, we're not talking about time, but the charge will depend on that overdrive factor. Like we mentioned about diode. If you get a diode there, you got something like that, you got start from there. It's the same thing that the bipolar transistor also has a PN devices. Then you are the MOSFET. The overdrive factor will cause the overdrive factor will cause higher saturating time, and then it will take a longer time to come back to your one. The lower saturating time, higher saturating time, it will cause the higher that overdrive factor, the higher will be the saturating time. It will be saturated for a longer time. It will need more time to recover. And if you got an IGBT switch, what is an IGBT switch? IGBT is a mixture of that we talked before. IGBT is a mixture of that, was a blend of that, the more bipolar and a bipolar and a MOSFET. That one, this device, you got you got a bipolar, you got this, you got this collector, emitter, and a gate. Collector, emitter, gate. This time it looked like a bipolar. This looked like a gate there. This is since you are applying a gate to this gate to the emitter voltage. Okay, gate to the emitter voltage, that is a voltage control device or voltage dependent device. MOSFET is the IGBT. That is this very common device in power electronics application. That is a very promising switch, or this is the switch to be used. Now with the future coming up, if you look to the chapter 1, the future coming up with this silicon carbide devices, that may change the MOSFET. The scenario will change. MOSFET with this silicon carbide, you can have a MOSFET, say 100 amps. MOSFET with a 100 amps MOSFET, 100 amps MOSFET. As of now, you can get say 1,000 volts. The kV, the 1,000 volts, you got like a 10,000, 100, what 100 kVA, like a volt ampere. But on the silicon carbide, the possibility of 100 amps. Now this has a, if you look through that, this the physics, what you call the periodic table of that, or called the field intensity of the silicon carbide, you can have about 10,000 volts a MOSFET. That means if you got a 10,000 volts MOSFET, you can see how much you can go. 1, 2, 3, 4, 10,000 volts, you will be got a mega volts, mega volt ampere. That's why with this future, with silicon carbide devices coming in the picture, the whole scenario may change. But as of now, the IGBT is the future device. Then will be IGBT and MOSFET, another one there. That's the one. IGBT is a voltage control or voltage dependent device. That's the way. Peak power loss. The peak power loss tends to occur in the switch in when? During the transition time. We mentioned before when that during the transition time, when it is going from on to off to off, that's the one. You remember that when that one is a on to off, that's the time when it is during the on time, the voltage is falling, the current is rising somewhere there. This is the voltage, this is the current. V by I product. The V by I product becomes when the maximum happens, when they're somewhere in the middle of that. That's why during the transition time, the peak power happens there. The lowest power happens when, this is obviously when the device is completely off. When the switch is completely off, the occurs when the switch is completely off, fully off. That's the one. There is an on and off, and then also there is a transition. These are 3 period come there. The internal junction capacitance of a transistor limits the dV by dt of a transistor. Yeah, of course, the internal transistor, remember internally, if you have a capacitor, internally if you got the transistor, if you got a transistor there and internally, it's an internal built-in capacitor there. If you apply a certain dV by dt, the current through the internal capacitor or junction capacitor, I through the junction capacitor, C dV by dt. If you apply this too much dV by dt, this the current, the junction current through the junction capacitance could be extremely high damage. That dV by dt is limit those internal capacitance. Excuse me. The average power loss across the transistor, the average power loss, you can find out that it asks you, once you know the current, you can find out the current. Once you know the current, you know the voltage across it, you can find that V, and I will give you the power from this part. And similarly, if you know the base current, you know the base to the meter voltage, you know the voltage and the current, you can find out the power from the collector, power to the base, that will be steady state power will be coming from there. Okay, parallel, sometimes the one transistor cannot provide all the currents you need. Sometimes you current them in parallel. Like if this voltage is 0.3, if this is 0.25, then there is a problem. There will be some current will go through the lower one, and then there's not the other one. As a result, what you do, you very often you put some resistance on the emitter circuit so that it's balanced out. So if there is a mismatch, you balance out. That's why you need those the resistance to current sharing, the equal current sharing, so that the equal sharing of the current almost. But you're not talking a very large current. No, you're not talking about a large resistance, very small resistance, ohms or million, so that it matches that. Okay, but if you give it too much resistance, then the current will not be. There will limit the current there. But you give this for matching, just to the imbalances you have in the internal characteristic. Now, sometimes you have also a couple inductor. Sometimes you use a couple inductor. Did I miss one? No. Did I use a couple inductor? Use this, that the dynamic sharing. If during the transition time, the steady state condition, you put a resistance, but in the dynamic condition, you also often use an inductor, because the inductor limits the change of the rate of change of the current. The current quickly cannot change. That's why very often you use the inductor to limit the dynamic current sharing, and the current it cannot change suddenly. You can have a situation like one transistor is taking a more current and more current for some reason, and the other transistor take a low, and then to make these balances, you can put an inductor so that the current doesn't change slowly. It's called the dynamic sharing. Use the inductor. What you do, like sometimes you use the snubber dV by dt, protect that. It's very important. Like if you got a if you talked before, like a transistor is one on. If a transistor is on, okay, if a transistor is one on, and then suddenly you apply there was a freewheeling action there. There was a freewheeling action was there from previous circle. The diode was conducting, right? The diode was conducting, and current was flowing through this freewheeling diode. Now in the next cycle, it was from previous cycle that the diode was conducting because of the inductive load, and then next cycles you turn on the switch. Once you turn on the switch, the moment you turn on the switch, suppose the transistor is turned on immediately and the diode was conducting, it was like a 1. Like you see that current will rise very quickly, and then the dIdt, the current will rise very fast. It will immediately current will rise. Now the dIdt of this transistor will be very high, and that will destroy the device. What you do, you apply or you put a inductor, small inductor, very small one. It could be stray inductor. You ensure that result is what is going to happen now. Sorry, the dIdt now instantaneous ddt Vs by Ls, and that is the one should be make sure the dIdt is higher than that, is lower than that the transistor there, so transistor is not damaged then. Okay, so that if the transistor has 1000 amps per microsecond, and you have to make sure that you will protect that one. Okay? You have to make sure that if this is a 1000 you can handle, but you should make sure that DIDT doesn't go 100, probably less than, sorry, 1000, which should be less than 1000. Okay. Now, if you know that your VS, you know if the VS is 100, then this should be less than, it should be less than 1000. Then you can find how much LS you need. You have to guarantee that. That means that basically LS is used to limit the DIDT of the transistor switch. The snubber capacitor. You also have a capacitor need. Why you need a capacitor then? The capacitor you need suppose you have you go there, you got a switch there, and the capacitor you have a voltage at 200 volts you have. Once you have 200 volts there, you are not turning on the switch, the transistor is off. Once your transistor is off, what you do, you go turn on the switch. Once you turn on the switch, look at that. Although there is no current here, there is a connection there. The voltage, the capacitor is going to see now, is going to charge. Capacitor is going to see a voltage, or this across this. The capacitor will be very much short at the beginning. As a result, the device here is going to see a large dB by dt. Suddenly it has no voltage. Suddenly it got 200 volts coming like instantaneously. That will damage that device, dB by dt. What you do, as a result, you put a capacitor there across it intentionally. If you put a capacitor across it, the capacitor will try to pass current through that, and it will slowly charge. Remember, the capacitor charges slowly, exponentially, and then it will charge through this R. It will charge through this R. The R and R is charged. It will go slowly. That the voltage across the capacitor rises slowly. dB by dt will be slow there. That's why you protect that device from dB by dt. The CS is used to protect the dB by the transistor. Okay. Now you may ask a question that what happened to this? Look at that. When you're charging very quickly then. Okay, you're charging very quickly through this diode there. When the capacitor is charged, when that next time the transistor is on, the capacitor will discharge through that resistor. Okay, discharge resistor. And then that if you don't have this RS, capacitor will discharge very quickly, but the discharge will be done through the transistor. The current will be too much, it will be damage the transistor there, because you had the CS to protect the device. When you turn on, it will destroy the device. Not to destroy it, you put the RS so that if the capacitor has a 100 volt, and then if the transistor comes on next time, divided by RS, will be the current will be through the transistor, so that you limit the discharging current of the capacitor. As basically one of the things you need to do, you always has to have it's a transistor, is a semiconductor device. Then when you have a current flowing through that, and there is a resistance internally, there is a drop, there will be power across the transistor, and as a result, that power has to go away. And then it will be junction internally. The manufacturer will tell you the junction temperature is allow for that, and there will be junction to case. Internally, case depends on how it is manufactured. There are different shape. There will be the case temperature. From case to the sink, normally power transistor you mount in a sink, heat sink, and then once you put it in the sink, then the sink will be filled and it will dissipate the heat, and then it comes to this. It comes to the sink. Depends on how this is case to the sink, how it is mounted, and if sink to the ambient. Like to the ambient, the ambient temperature is no. The sink to the ambient, the depends on how that thermal resistance. That means that is it a cool, is it a air, or is it a fan or blow? These are the thermal resistance you need to that. The maximum permissible power dissipation is you can find out what is that. If this is given, Tj is given, Ta is given, Tjc is given, that is given there, and there are some examples in the book, but review them and please try to find out what is the right answer for that. This is very important. That's the heat is the biggest problem. Think about it. If you have a 1000 amps device, okay, 1000 amps, a device, a current through either a transistor or diode or whatever this one, you are having the drop of the across is a 1 volts. Okay, drop is 1 volts across the device. You know that 1 volts is not a much. It's like we got a kilowatt. You know, you have to dissipate 1 kilowatt of that device. It's very easy. It's not only 1000. Sometimes you got a 4000 device. Okay, you've got a 4000 amp. If you have even a 0.5 volts, you know, you cannot have a 0 volts. You know, these are finite, you know, the devices. Then you can have a 2 kilowatt. And that's the biggest challenge to get rid of the heat. And the heat is the one is going to destroy a device. Okay, please calculate that number. I think that's the end of this the presentation. Please, as I mentioned to you, please review these MathCAD files. There are some videos before you read this one.